Piesakot nākamo runātāju un šo tēmu, es pirmkārtām gribu ieraudzīt zālē Madli. Ir, jā, paldies. Piesakot nākamo runātāju un šī tēmā, kur es lasu, kad Nacionālā mēroga ekosistēmu stāvokļu pakalpojumu kartēšana Igaunijā. Es pēkšņi sarosījos, mums ir 2 pilotu teritorijas Igaunija atkal priekšā Nacionālā mēroga kartēšana. Es ļoti ceru, ka mēs visi dzirdēsim atbildi, kā tad īsti ir Igaunijā, un vai tiešām atkal ir labāk nekā pie mums. Ja? Tad Madli Linder no Igaunijas vides aģentūras.
Thank you for inviting me. My name is Madli Linder, and I work in Estonian Environment Agency. And I'm going to introduce country-wide actions of mapping and assessment of ecosystem services and ecosystem condition in Estonia. Among all the international biodiversity and ecosystems related obligations and goals, the basic document regarding biodiversity protection in Estonia is Estonian Nature Conservation Development Plan that also obliges us performing assessment and mapping of ecosystem condition and services on national level. And mainly for moving towards achieving these goals, the project called ELME was initiated that I am leading, and my institution also. So in the course of this ELME project, the main action that is going on this and the next year, for which we have contracted 2 universities and have gathered a working group from different governmental institutions, is creating methodology for countrywide mapping and assessment of ecosystem services of 4 major ecosystems that are grasslands, wetlands, forests, and agro-ecosystems. So we are doing the 3 main blocks during this project. We are creating base map, then we are assessing and mapping ecosystem condition, and then ecosystem services. We are assessing and mapping potential supply. We are mapping it in spatially explicit way in a resolution of 10 to 10 meters, and all this work will be countrywide. We'll create methodologies which will be agreed with stakeholders, and finally the system will be made available for users, including decision makers. So first we have to define ecosystem boundaries, that is creating a base map. We first create individual ecosystem base maps, ecosystem by ecosystem, and then we consolidate them. The base map gives us the boundaries and the extent of ecosystems, and also the geographic reference to the ecosystem condition and ecosystem services. So we have to set up the rules to define these ecosystems and their borders, and then the rules to which ecosystems are more priority ecosystems than the others, to consolidate the final map. Because we want the classes on the base map to be mutually spatially exclusive, no overlaps, no gaps, also ecologically relevant. The classes will not be land use based or something like this. The classes must be mappable, data must be available, linkable to other classifications like other internationally and nationally relevant classifications, and of course the classes must be understandable for decision makers. So this is an example of the workflow for grassland base map. The rules are quite complicated, but we need the rules to prioritize the different databases that we use, because all these databases are somehow relevant, and we try to use this all. Like for grassland space map, we have two main broad classes: historical semi-natural grasslands and other grassland types that are also divided into subtypes, in total of 14 subtypes. And this kind of complicated rules are also for forest, agroecosystems and wetlands, and also to distinguish between different ecosystems. The next step is defining and mapping ecosystem condition. We have had many debates on what is condition and what is good or reference condition. Is it what it was before human impact, and then when before human impact? Is it naturalness or something else? We define the condition and the respective classes for each ecosystem on the basis of the amount and duration of human impact and the knowledge level of it. So it's kind of naturalness, yes. And the classes differ in capacity to provide different ecosystem services and the potential supply of specific ecosystem services. And here you can see the parameters we use to define different classes for different ecosystems. We don't use complex formulas, but these parameters that we have chosen for each ecosystem. And for each of these parameters, we use many different kinds of data sets and data layers. For example, historical habitat continuity that we use as a parameter for forests and grasslands. We use as one input the continuous forest areas that are identified in the help of machine learning or artificial intelligence and historical maps. And for example, overgrowth rate that we use as input to define grassland classes, we use LiDAR-based maps. On the basis of the LiDAR data, we can differentiate different height classes of bush and tree layer, and on the basis of proportion of these different height classes, we can use this information as input to define different grassland condition classes. And for example, for forest, we use also cutting information that is derived from Lancet and Sentinel imagery on the basis of the differences between different years detected on this imagery. About the ecosystem services. We have chosen about 32 ecosystem services. For provisioning services, we have, until now, we have chosen about 15 of them. The list is not totally complete yet. For regulation and maintenance services, we have chosen about 10 services. Here's an example of how we calculate pollination index. For pollination service, we use habitat suitability, the pollinators, considering characteristic plant species, their nectar productivity, and the length of the flowering period, also the distribution of wild pollinators, landscape metrics, and data on pesticides. And this is just an illustration to show some of the indicators we have calculated, like wind energy or surface roughness, that can be used to estimate different other ecosystem services or soil erosion. From cultural services list, we have chosen about 9 services. This is the most confusing group for us. We are struggling with defining the potential supply that we try to estimate. It's hard to exclude the demand and include, for example, the limiting factors, like for hunting, the hunting limits. And all these services are still under discussion. And in the case of the cultural services, often the case is soundness of existing databases. This is the example of the distribution of sacred natural sites. Which sites are considered the sacred natural sites depends largely on the perspectives of different stakeholders. In Estonia, we have, in addition to ELME project, we have many other projects that are over or lasting at the moment. This is a short list of them and what is done in these projects, including natural capital accounting projects that are done by our statistical office, Statistics Estonia. And in addition to these, Estonian Ministry of Finance is leading the maritime spatial planning process, and in this process they are also using the materials of ecosystem services that were also modeled and mapped under ELME project. And this is an ongoing process. They are also providing a web tool. They are testing it at the moment, and it will be publicly available. So the challenges we have in Estonia. All the countrywide actions have been mainly project-based so far. They are nationwide, but project-based, and this is quite a huge challenge. And at the moment, we are trying to create one whole system of all these different projects, and as well as from different approaches. Like for us, a huge challenge is to harmonize the approaches of natural capital accounting and so-called bias approach that we are doing in the course of ELME project, including setting up the clear definitions, what we are measuring. In the course of NCA, actual flow is measured that is equal to the use of ecosystem services. But for MAES approach, And in the course of ELME, we are measuring the potential supply of ecosystem services. And what we are doing both at the same time is we are mapping the ecosystem extent, which is quite hard to make harmonize also. And of course, technical issues or challenge for us, the calculation capacities and so on, and of course bureaucracy, like procurements, like for ELME project, the main work we are doing now, the procurement lasted 10 months. That is not quite normal. And of course, integration into decision making is crucial. And also, with the integration into decision making is related future accessibility to the data and methodologies, and understandability of these, reliability, repeatability, etc. And one more challenge is integrating different data sources and methodologies that are being developed at the moment, but are not yet there in the future to this whole system. And I would like to thank all the ELME team, especially Ain, Miguel, Villoslada, and Helm, who have contributed into this presentation. Thank you.